this computer. All right, you're good to go.
Cool. So, yep, my name is Matthew Cooper. This is a little introduction to ray tracing with TypeScript. I'm going to be jumping between slides and code pretty regularly. Also, I'm an instructor here at PDS Code Guilds. I teach the Python full stack class, which is web development with Python, HTML, CSS, JavaScript, and Django. It's super fun. You should check it out. These are a couple of renders that I've made. I didn't make these with the TypeScript ray tracer. I actually made them with a Java-based ray tracer that I wrote. This one on the left, you can see you've got a mirror sphere, and then we have a glass sphere, and then just a matte sphere. And then on the right here, this is an 8-dimensional cube that I projected into 3-dimensional space. So I love hyperdimensional geometry. Feel free to ask me about that in the question section. But you can do ray tracing with hyperdimensional geometry as well, and it is fun. So a quick dichotomy, rasterization versus ray tracing. These are two major 3D rendering algorithms. So rasterization, we represent shapes as triangle meshes. And then basically, the basics of the algorithm is that we sort them in back to front, and then we draw them from back to front. So the last one that's drawn is the closest, so it'll be on top of everything. And that's used in a lot of more real-time applications like games. There's a really cool framework called 3.js, which uses rasterization if you want to do 3D graphics in the browser in real time. Ray tracing, we basically trace a bunch of rays around a scene. It's a little bit more computationally intensive, but it's easier to capture complex phenomena like reflection and refraction. So reflection is like a mirror surface, and then refraction is light bending through a medium like glass or water, which has an index of refraction. You can also capture really cool things, like we were talking about God rays, which it's usually called participating media. Basically, there's some stuff in the air, and the light is hitting that stuff in the air and then hitting your eye. So if you want to render things like smoke and stuff like that, it's much easier with the ray tracing. And there's lots of different kinds of ray tracing algorithms. There's forward ray tracing, which is you basically trace rays of light from a light source into the scene, and then eventually it hits the camera or the eye. People don't usually use that because it's really computationally intensive, because most of the rays that are being traced around never hit your eye, right? They just kind of bounce around the scene and just dissipate in energy. So it's not really commonly used. Backward ray tracing, we basically start from the camera or the eye and then go backwards through the scene and try to figure out the lighting from the light source. And then within that, there's kind of two major approaches: direct illumination and path tracing. So direct illumination is basically you trace a ray from the camera into the scene, and then the first object you hit, you try to calculate the lighting on it. And then path tracing, you actually continue bouncing that ray around until you eventually hit a light. And direct illumination is obviously a little bit more quick to compute. Indirect illumination is slower, but you can capture things like color bleeding. So color bleeding is like if you have, if you were in bright sunlight and you held up like something that was really red close to your face, you'd actually see red on your face because light would bounce. It would come from the sun, hit the red object, then hit your face, and then hit whoever was looking at you. So you get that's called color bleeding. Anyway. And you can get really cool things like indirect lighting with path tracing. We're going to implement a direct illumination ray tracer. Then there's also bidirectional path tracing, where you trace rays from the camera toward the light, and from the light toward the camera, and then you can combine those paths in different ways. Photon mapping, you basically trace rays of light through a scene, and then you just store them on diffuse surfaces. Anyway, we could go on. Metropolis light transport, super fancy too. You can look up those terms if you want to. So here's kind of an overview of our direct illumination algorithm. So we've got a camera, we've got an image, and then we have an object that we're hitting. So we're going to basically generate a ray from the camera into the scene through a given pixel in the image. We're going to find the closest intersection of that ray with an object in the scene. And if the ray doesn't hit an object, we'll set the pixel to black. And if it does, we'll trace a ray from the point of the intersection toward a light source. And if it's blocked, like this ray is, then we'll set that pixel to black too. Right, because this ray came down here, it hit the surface, and then it tried to trace a ray to the light, and it was blocked. So this is a in shadow. But then if it's not, if the shadow ray is not blocked, then we can use the material properties on the object to compare, to figure out what the lighting should be. Basically, how much light came from the ray toward the direction of the camera through the pixel. And just a little bit about TypeScript and why I chose TypeScript for this. It's a dialect of JavaScript that adds static typing. So I'm a big fan of static typing. It just gives, you can see here, it makes code a little bit more rigid, but it also makes it more explicit and predictable. And it can give you like really clear error messages. Basically every variable has a type. So you can see in this example, we have a function that takes two parameters a and b, calculate the sum, and return it. So we can actually pass this function two numbers, or we can pass it two strings, and it'll just be happy either way. It doesn't care what the types of the variables are. So the TypeScript version, we actually declare the types of the parameters and the type of the return. So we say this function add is going to take two parameters a and b. They're both numbers, and we're also going to return a number. And then here we declare a variable c, and we also say this variable c is a number, and we sum those two. So when we call this and try to pass it two strings, it'll actually give us an error. So that's good. That's good. Because if you call a function and you accidentally pass the wrong parameters in vanilla JavaScript, it might not crash. It might crash in some arbitrary place inside the function. It would give you a very ambiguous error. Whereas with TypeScript, if you pass the wrong parameter to a function, it'll tell you immediately that you passed the wrong parameter.
I have a quick question about that.
Yeah, what's up?
So, so where it says let's C colon number equal a plus b, I'm just curious, is that basically syntactic sugar over JavaScript objects?
I don't know if I would call it syntactic sugar, but yeah, it does. So TypeScript is a dialect of JavaScript. Basically, you run TypeScript through a preprocessor, which is a little bit of code, and it'll turn it into JavaScript, which then can then be run by the browser.
Right. I just meant is C number basically just a JavaScript object behind the scenes and without the curly braces?
No, C is just a regular. It's just a regular JavaScript variable. And then when you you compile the TypeScript into JavaScript, it'll basically do all the checking for you. So it's not a special object.
Okay.
It's just a regular JavaScript object. Yeah.
Gotcha. I was wondering about the coercion. If those, like the A and B in the last line, were actual numbers but still strings, would it do the coercion and accept that, or would it just say no, you can't do that either?
No, it wouldn't. It wouldn't.
Okay.
Yeah, that's one of the weird parts about JavaScript, right? Is it does that type coercion. So no, it would just give you the error still. It's a good question. Okay, and the reason I chose TypeScript, it scales really nicely if you have a lot of code, and also ray tracing is naturally pretty object oriented. So looking back at this previous view, we're basically going to break this whole scene into different classes. So there's going to be a camera class, there's going to be a shape class, a light class, a ray class. So I think ray tracing really exemplifies the power of object-oriented design. So hopefully the code will match that. Okay, so really quickly, there's some geometric primitives we have to cover. There's points, vectors, normals, and rays. So a point is like a position. A vector is a direction. A normal is a vector that's perpendicular to a surface. And this is actually going to be important later on because we're going to have to transform them in a specific way to make sure that they're still perpendicular to the surface. And then array is a combination of a point and a vector. So it's got a position and it's got a direction. That's what array is. Let me switch over to my code really quick. So let's look at geometry3.ts. So all this code it's hosted in our Tech Talks repo. I can definitely post that to Slack. Oh, let me just do it right now. I have a link to it up here. Not to Slack, to our chat. Here, I'll even copy this one. Okay, so there's all the code if you want to check it out. I'm a big fan of getting a hands-on experience. So yeah, we've got a, I created a tuple3 class. Tuple3 is basically, it's just a 3 numbers. We got X, Y, and Z. Because all these, points, rays, normals, they all have 3, not rays. Points, normals, vectors all have 3 numbers associated with them. So here we have the constructor. I added some static methods. I don't even use these. So let's just avoid those. Anyway, so tuple3 just has 3 numbers in it. And I just did that so I don't have to reinvent the wheel 100 times. And then the point3 class has, it extends tuple3. And it has a few methods like distance squared calculates the square of the distance between 2 points, and then the distance just takes the square root of the squared distance. And I did this just because sometimes you do want the squared distance. And square root's also very computationally intensive. You don't always want to do a square root.
If I may, I noticed you're using, dx, dy, z calculus stuff. Are there, in fact, any calculus methods available to that math class?
No, this isn't calculus. It's just the difference in the x, the difference in the y, the difference in the z.
Okay.
It's not like
I guess I should have said differentials, not. I'm sorry, I know what you're saying, though.
Yeah. So it's just the difference in the x, y, and z directions. So let me actually step into our next slide before I move on. Slide, view, present. So just really quickly, if we're talking about 2D, these are the forms in 2D. So the difference between 2 points, the distance, is take the difference in the x, the difference in the y, and square them and sum them up. So this is just, you can derive this from the Pythagorean theorem. And then the length of a vector is the square root of the sum of the squares of each values. And oftentimes we'll want to normalize a vector. So normalizing a vector just means dividing it by its own length. And it'll make the vector so that it's a unit length. So the length is 1. And then there's also something called a dot product. A dot product, it's pretty simple to calculate. If the dot product between 2 vectors A and B is just it's the sum of the products of each of their components. So ax, bx plus ay, by. And intuitively, that is it's actually the cosine of the angle between them. So later on, we'll need to calculate the angle between 2 vectors, the cosine of the angle between two vectors, and this will allow us to do that. So just really quickly in the code. I created a direction3 class. I don't know. I wanted to make it easier to calculate these things between vectors and normals. So maybe this is a little over-engineered. But anyway, we got our same constructor. We inherit from tuple3, and then there's length squared length. I also have these functions for scaling the vector, so just multiplying each of the xy components by a value. Normalizing, we just divide by the length. and which you calculate up here. And then the dot product is pretty simple to calculate. It's just the sum of the product of the components. And then there's two classes, vector3 and normal3, and they both inherit from direction3. Anyway, and then there's ray3. So rays have a point and a vector, so O and D. And then we just got a constructor for it. And then here we actually calculate the point along a ray. So this is super important, actually. You have the origin and the direction. Let me go back to the slide. So yeah, for this ray, we've got the origin and the direction. Then we can actually calculate any point along that ray using that formula, the origin plus t times the direction. So that's basically how we're going to calculate the intersection of that ray with objects in the scene. Okay. And then really quickly about transformations. So here's a few really simple forms of transformations: translation, scaling, and rotation. So translation is we're basically we're just adding a value to x and y, so we can move things around. Scaling, we multiply by value, and then rotation is a little complicated. We basically have to include both cosine and sine and the x and y values. But this will rotate a point about the origin by theta degrees. So those are the formulas for calculating each of those. And it's easy to actually represent those in matrices. So we can represent points, vectors, and normals as 3x1 matrices. And then we represent transformations as 3x3 matrices. So this is just for 2D, of course. We're not in 3D yet. To transform those points, we can basically multiply it by a matrix. So here in this example down here, for example, here we're scaling, right? So if y'all remember how to multiply matrices, here's the formula up here. It's a little complicated, but you write it once and then you just can use it repeatedly. So yeah, what's up, Stephen?
If I may, you're basically multiplying I took linear algebra, you're multiplying the rows in the left matrix by the column in the right matrix, and then adding those together.
Yeah. So here we have like xy1. So we've got a point, and we're multiplying it by this matrix with these m00, m01, m02, and so on. So you can say, really, I don't know how to describe this. We just take this and you just turn it horizontally and just multiply it across there. So you get xm00 plus ym01 plus 1 times m02. And then you just do that for every row. So that would be the intuitive explanation. Anyway, so yeah, we're just taking these transformations from this previous slide, and we're representing them instead as matrices. Happens every time. Happens every time. Pete, can you mute? Thanks.
Got it.
So yeah, anyway, so we can represent these transformations using matrices. We just got to plug in the values. And then we can just write some code for multiplying each of these different points, vectors, and normals by the matrix, and we'll actually transform it. So this is really used for moving basically transforming between different coordinate spaces. So you can say, going all the way back to here, right? We're basically going to have a coordinate space for the camera, and then we'll use a transformation to go from the camera's coordinate space into the world's coordinate space. And we'll have a coordinate space also attached to the shape and a coordinate space attached to the light. So we can basically, it's basically allowing us to like move these things around, right? So if we can translate the camera back, so when we generate a ray and we translate it into world space, it'll actually be further back in world space. We'll see that in the code. anyway, and then so we have these transformations, and here are the matrices in 3D. So they're a little intimidating, but basically, translation's pretty simple, scaling's pretty simple. Rotation's a little bit fancy because there's actually in 3D space, there's 3 different versions of rotation. There's yaw, pitch, and roll, which are aeronautical terms, I believe. And so yeah, you can rotate about any axis. So this first one, this will actually rotate in the XY plane or around the Z axis. So this first one's yaw. This one rotates in the this one rotates about the Y axis in the XZ plane. So this would be pitch. And then this last one rotates around the X axis. So this is roll. So yaw, pitch, and roll. So we can use these to actually rotate the objects in 3D space.
Sorry, could I ask a quick question?
Yeah, what's up?
Which, I guess what I should be asking is where are the angles alpha, beta, and gamma? Like which ones do they correspond to, I should say?
Alpha would be the angle that we want to rotate around the Z axis. Beta is the angle that we want to rotate around the Y axis, and gamma is the angle that we want to rotate around the X axis.
Okay.
Yeah. So, we can orient our objects in 3D space. So yeah, let's look at the code for these transformations. The code is a little bit brutal. I adapted it to some old code that I wrote a while ago. I'm not super proud of it, but it gets the job done. And at the end of the day, that's what's important. I actually have it hard coded. I don't know. I didn't want to write loops and stuff like that. Loops are actually, I don't know if you all have heard of unraveling a loop. Unraveling a loop is like if you have a loop that goes over, it's always looping 5 times. Why not just write the code 5 times, and then you don't have to have the iteration step. So it's a little more computationally efficient. But anyway, it's not pretty though. So got a class matrix 4x4. This represents a 4x4 matrix. I've got all the values out here. Very tediously listed. I wrote this other class that I was thinking of using that actually used a 2-dimensional array. So if you want to go that route, you already got some starter code. But anyway, so it's a bunch of hard-coded stuff. Identity matrix just basically doesn't change anything. It's just got 1s down the diagonal. Oh yes, and I forgot to mention if you wanted to compose transformations, so you wanted to translate and then rotate and then scale, you could just take the matrices that represent those transformations and multiply them all together, and then you just have one matrix that can transform points, vectors, and normals. So here's just a function for multiplying 2 matrices. Oh God, is it hideous? Let's move on. And here's a nice formula for calculating the inverse of a matrix. Anyway, so I have this other class transform3, and this actually contains both a matrix 4x4 to represent the transformation and a matrix to represent the inverse. Because oftentimes we'll want to transform something, but oftentimes we'll want to invert it. So the inversion is the opposite of the transform. So in terms of our objects, basically, a transform will take us from object space into world space, and an inverse will take us from world space into object space. So that's what these do. So coming down here, I have a few little methods like set as scalar. So that sets, you can scale by X, Y, and Z. I set those along the diagonal of the transform matrix, and I set the 1 over those numbers along the diagonal of the inverse matrix. Set as translator, I set X, Y, and Z down that column of the transform matrix right here. And I subtract the negative. I set the negative down the rightmost column of the inverse matrix. And then rotation, I have a few things for setting rotation around a particular axis, and then here's a general set as rotator, rotation around the XY plane, XZ plane, or the YZ plane. Anyway, so basically these methods will set the, they'll set up the transform as a particular, rotate or translate or something like that. And then I have some methods here to take a point vector normal into world space or take it into object space. And again, these are just the formulas that we kind of looked at before. They're basically this formula, multiplying that point vector normal by the matrix, but just hard coded. Yeah, fun stuff. And I can't really get into it just because I barely understand it, and also it's pretty complicated. But for normals, you actually have to multiply by the the transpose of the inverse to make sure that it still points in the direction opposite a surface. I don't know. And I remember reading a long article about it, but I don't really fully understand it. So basically we have these functions. They can take, two world space, can take a point vector or normal, and then it'll return a point vector or normal that is transformed. Again, yeah.
So you have the point vector and normal in those functions. What's the any supposed to cover?
Oh, so the way TypeScript works is you can, this is called method overloading.
Yeah.
If you're all familiar with Java, yeah. So in TypeScript, you're not allowed to, you can do method overloading, but the actual implementation has to basically cover all of them. So
and so you've got any as kind of a
it's a catch-all.
Kind of a lazy catch-all. I guess there's supposed to be a way to combine those three different types into the same type.
Well, you basically have to cover all your bases. So going back to maybe like some of this code. So this let's look at this tuple3 to kind of look at that. So this constructor, I basically wanted to overload the constructor and have two different options. One option would be to create a tuple3 from an existing tuple3. And the other option would be to create a tuple3 from an X, Y, and Z value. So I wanted to cover those two things. And to do that, I actually have to, I can say I can take a tuple3 or I can take three numbers. But then this last one, the implementation, has to cover all those cases. So X here has to be any because it could either be a tuple3 or a number. And then Y and Z, they can be numbers, but they have to be optional, which is what these question marks mean.
I mean, this is kind of a nitpicky kind of thing, but I'm wondering, so TypeScript is supposed to be strong typing, strong typed kind of JavaScript. Doesn't this, I don't know, obviate that?
The any part?
Yeah.
Yeah, it does. It definitely does.
Okay.
I don't know why they chose this. I'd love, it's like how, in C# they added var to C#.
Oh yeah.
It's static typed, but if you want to go loosey goosey, you can go ahead. So,
yeah, I gotcha.
Yeah, unfortunately, TypeScript's pretty limited by, its basis in JavaScript. So it tries to improve things, and it does, but it's still not quite there.
Out of curiosity, how else is TypeScript used besides for rasterization? Like, what other applications has it been used in?
Oh, TypeScript's used all over for like web development. It's probably the most popular. Really? I don't think I've seen any other people use it for graphics algorithms, but yeah, TypeScript's very popular for web development.
Anything that you might use JavaScript for, you can use TypeScript for, pretty much.
Wow.
Yep.
Sounds like I better learn TypeScript then.
Yeah.
It's pretty cool. Yeah, if you want to use something like React or Angular or Vue, if you use them on the CLI, you do have the option to actually build the project with TypeScript included. So yeah, it's pretty cool. It's pretty cool, and it's just something. It just scales better. It's one of the problems with JavaScript. I don't know. JavaScript, for some godforsaken reason, you can call a function and you can pass the wrong number of parameters, and JavaScript will just go on just all happy-dappy. So anyway, so yeah, this part, it just does the transformation. You don't really have method overloading, proper method overloading in JavaScript. So in TypeScript. So what you have to do basically is you can say this method can take a point, a vector, or a normal, or anything. And then in here in the actual code, you have to actually check the type of what you're getting. So it's a little annoying. But basically here we check if it's a point or a vector or normal, and then we transform it and return a new normal, vector, or point. And those formulas are out there. I'm going to point to some references, some resources after the presentation, if y'all want to like look up the nitty-gritty mathematics. It's one of those things I like to kind of gloss over because it's like you write it once, you make sure it works, and then you never look at it again because it is a little tedious.
Yeah, 2 words, linear algebra.
Yeah, it's all linear algebra. Cool. So let's talk about our camera model. So our camera is going to be basically at the origin and pointing down the z-axis. I'm using a left-handed coordinate system. There's left-handed and right-handed. Left-handed is basically the your thumb's your x-axis, the pointer finger's your y-axis, and your middle finger's the z-axis. So that's kind of how you can visualize our camera. So we're at the origin, we're pointing down the z-axis, and then we have our image plane. So given an XY coordinate on the screen, we can generate a ray from the origin to that pixel. So let's go look at that code really fast. Oh, that's in camera. I was smart and broke it up into multiple files. I don't know, I wrote an interface. An interface is like, it's like an abstract class, but you can't have any properties. I don't know, does anybody have any questions about interfaces and stuff, or abstract classes? Everybody know what that means?
I think it's probably the TypeScript equivalent to maybe Ruby's procs and lambdas and all that, if I'm not mistaken.
No, I think lambda is usually it's a functional programming thing.
Oh, right, okay.
An interface, so an abstract class, it's a class that you can't instantiate. Basically, and you can have methods in that abstract class that don't have implementations. Those methods, if you inherit from that abstract class, you have to implement those methods that haven't been implemented yet. An interface is like an abstract class, but it doesn't even have any properties. So it's really just a list of methods. And then if you implement that interface, you have to create an implementation of that method. So here I have an interface camera and a generate ray method. So here's my implementation for it. And I don't know why I did that. I think maybe down the line I would add additional cameras like an orthogonal camera, orthogonal projection. I've seen people also make spherical cameras, which are cool. So you can actually I don't know, you can get like a fisheye effect. But anyway, I just leave this line of code. It's not useful. So here, this method is just given the x coordinate of the pixel, the y coordinate of the pixel, and then the width and the height of the image. And here I basically do 2 times the x coordinate divided by the width minus 1. That basically puts everything, the whole image between -1, -1, and +1, +1. Right, because if it was 0, 0, 0 would be basically mapped to -1, -1. And then say if it was a 300 by 300 image, right, 300, 300 would map to +1, +1. Because this would, 300 divided by width would be 300 divided by 300 is 1, 300 divided by 300 is 1. 2 times that minus 1 would still be 1. So it just basically puts the entire image between -1, -1, and +1, +1. And then here I just literally generate a new ray, starts at the origin and points to that XY coordinate. And then I use the focal length that actually will control how much perspective you have. So that's that z-axis. That's how far away from the origin that we're actually projecting. So that's this distance here. So you can kind of visualize that a little bit. And then I just take that ray and I put it into world space. I normalize the direction and I return it. So that's our camera model. Oh, time's flying by. Okay, and then the only shape I implemented, just in the interest of time, was a sphere. Basically, the way you can calculate the intersection of a ray and a sphere is by substituting the coordinates, the components of the ray into the equation for the sphere. So if you have equation, any equation of x, y, and z, you can always do that. You can substitute that, and then you just need to solve for t, and you can figure out where along the ray it intersected the shape. So here we got O plus T times D. That's the formula for the ray. Here's the formula for the sphere. X squared plus Y squared plus Z squared equals R squared. So we just take the components of the ray, OX plus TDX, and then just substitute it into the X, Y, and Z value. So we got OX plus TDX squared plus OY plus TD dy squared plus OZ plus TDZ squared equals R squared. Anyway, you do FOIL. You all remember foiling, first, outer, inner, last. And then you can rearrange it and basically get it into the quadratic formula. So we've got, AX squared plus BX plus C equals 0 is the result. And then we can actually, use the quadratic formula to solve for T. And this will tell us where along the ray it intersected the sphere. And there's 3 different possibilities here. And the quadratic formula can give us three different results. So because if the quantity b squared minus 4ac is less than 0, it doesn't have any real solutions. So that's the case when the ray actually misses the sphere. And then the ray could touch the sphere tangentially. That's the case when b squared minus 4ac is 0. And then the ray could pierce the sphere, which is the regular solution when b squared minus 4ac is greater than 0. So there's 3 different possibilities, and then we'll get 3 different possible solutions. So let's look at our sheep. So yeah, we've got. Well, let's look at the sphere first, and we'll talk about the other things. So yeah, I have a shape interface. And I created this class coordinate system 3. Coordinate system 3 basically is it's a class that has a transform in it for transforming stuff. And then it has the 2 world space and the 2 object space methods. So yeah, so I inherit I have an abstract class shape extends coordinate system 3. And then I have a few methods, abstract methods, intersect with array, get some surface geometry, so information about the surface normal, and then getting the material. So here's my sphere. I just initialize it with the radius and the material. And then here's the intersection code. Basically, the method will take a ray in world space, and it'll use this to convert it into object space. And then it's the rays in object space, and then I calculate the intersection. I wrote this quadratic function. That's all the way in my RT math. Yeah, this is the little tedious, but this is calculating. It's doing the quadratic formula in JavaScript. So we calculate that b squared minus 4ac, and if it's less than 0, we get no results. So we return an empty array. If it's less than a certain threshold, we only get 1 result. So we just return, we assume that b squared minus 4ac is 0. So we just return negative b over 2a. And if it isn't, we take the square root, and then we have those 2 results, and then we return both of them. And we actually put them in order. So depending on which one's larger, it'll go last. You got a question, Stephen?
This might go off on a tangent a little bit. Is there a reason why you on line 6 you used t less than 0.0 instead of just the integer 0?
No. Well, in JavaScript, there's no integers. There's only numbers. So yeah, I could have written 0 there as well. I think I put 0.0 just because I adapted this code from Java.
Okay.
Maybe, I don't know, maybe it's a little bit more explicit. I don't know. But anyway, so that gives us basically the solutions. And then here I can check if I get any solutions. If the first solutions, this is a check to you. It's good to have like a little bit of a threshold. Because if you're like if you're very close to a surface, you can get numerical errors, like false intersections, especially if you're checking for those shadow rays. Remember, I talked about the shadow rays. Shadow rays you trace from the object to a light source. And if you just always check if it's non-zero, if it's greater than 0, then sometimes you'll get false intersections. So there's a little bit of a threshold. And I have this intersection object, which basically has the ray in object space, the point of intersection in object space, the ray in world space, the point of intersection in world space, t, the point along the ray it intersected the shape, and then the shape that it intersected. Anyway, and then I just calculate, the constructor just takes the two rays, the ray in world space and the ray in object space, and then I just initialize the points from those using the t value. Anyway, so we get t. So basically, if the first number is good, then we return a new intersection using those two rays, and then the t value, and then this is the shape, of course. And then if the second number is good, because I don't know, maybe we're inside the sphere, we'd get two intersections, but only one of them would be greater than 0. Then we just return the second t value. Otherwise, we return null, meaning there's no intersection. And then just really quickly, here's a little method to get the surface geometry. So I actually have another class, surface geometry, which contains the point of intersection, the surface normal, and the vector that points to the camera. And this thing takes an intersection object. So normals are super easy to calculate on spheres because you just take the point of intersection and you just normalize it. You just create a vector pointing from the origin to that, right? Because basically the surface normal is just pointing out directly from the origin. And then the light vector, I just initialize using the ray in object space's direction. And then I invert it. Anyway, okay, so that's this ray sphere intersection. The light source that we're going to use is called a point light. Point lights are probably the simplest light sources to use. They radiate light equally in all directions. And the intensity follows the inverse square law, meaning that the intensity at any given distance is inversely proportional to the square of the distance. So this is how gravity works. Right? If you go out a mile and test the strength of gravity, and then you go out 2 miles, you won't find that the gravity went down by a half. It'll have gone down by a fourth. And that's because the gravity is basically radiating equally in all directions. So it gets diffused. It's the same thing that works with the point light source. So if you had a flashlight or something like that, the intensity of light at a point is actually inversely proportional to the square of the distance. So anyway, so let's go look at we have a light interface as well, interface light. And that just there's an interface. You just give it a point, it'll give you back a light vector array. I don't know. A light vector is basically, it extends vector, but also includes a color. So it's a light and a color. Sorry, it's a color and a direction basically. And this point light class, it basically, here we take the origin and we transform it into world space, wherever the origin of the point light is. And here we're calculating a vector starting from the origin of the light to the point of intersection on the surface. Here we're normalizing it, or no, here we're dividing by the length squared of that vector. We're dividing the color of the light by the inverse of the length squared. So this is that inverse square law. And then here we're normalizing. the vector and returning a light vector. Okay, and okay, and then next we want to actually calculate the reflectance at that surface. So we're going to use Lambertian reflectance. So Lambertian reflectance, it's an ideal model of a matte surface, and it's one that reflects light equally in all directions. It derives from Lambert's cosine law, which is why it gets colder in winter. If you ever wondered, it's not because the Earth's further from the sun. It's actually because the northern hemisphere is tilted away from the sun, so that the surface area that the sunlight hits is lessened. So basically, it's the intensity of the incident, I should say light. Oh no. The intensity of incident light is directly proportional to the cosine of the angle between the surface normal and the light. So, right, if the sun's directly overhead, you get 100% of the light. But as the sun, gets lower on the horizon, you have less area that the sunlight's actually hitting, so you get a less intensity. So that's why you might expect this to say 100%, 100%, 100%, 100%, because I said it reflects light equally in all directions. But the surface isn't receiving 100% of the light all the time. The amount of the light that the surface is receiving depends on the angle between the light source and the reflected direction. Okay. So let's go look at that in implementation. It's pretty straightforward. Material. So I have, that should be there. So here I have an interface material. It has a get color method, and it takes the surface geometry and a vector pointing to the light, basically. And it returns a color. So here you can initialize this using a color. And here, this is pretty straightforward. I just take the color of the material and multiply it by the dot product of the light, of the vector that's pointing in the direction of light and the surface normal. So that's basically Lambert's cosine law right here, right? Because the dot product is the cosine of the angle between the two vectors. So that's all that does here. Okay. And finally, we're ready to bring it all together. So again, we're going to generate a pixel from the camera through the generate array from the camera through the pixel. We're going to find the closest intersection. We're going to trace a shadow ray from the surface to the light source, and then we're going to figure out the amount of light that was reflected from the light source to the camera. So here I have main.ts. So I created a scene class. I don't know. A scene just has a bunch of shapes, a bunch of lights, and a camera. And then it has this nice intersect with method, and that'll find the closest intersection given an array. So basically, we start off with an intersection and make it null, loop over our shapes, intersect the array with each shape, and then here's a little bit of a complex of an expression. But basically, if our original intersection is null, or this one's not null, and this one's closer, then we'll assign the IT temp to IT. So we want to find the closest intersection, the closest non-null intersection. So that's what this does. And then here we're creating our scene. So here we create a scene object. I create Lambertian reflectance. Oh, by the way, I made this like little just RGB color class, which just contains RGB values. And they're all between 0 and 1, or they're supposed to be. And then here's just a methods for adding and multiplying them. And then I have a few constants like black and white. So where's my main? All right. Okay. So anyway, I create Lambertian reflectance. That's white. I create a sphere with a radius of 100, and I push that into my shapes. my scene shapes. And then I create a perspective camera with a focal length of 4.0. And here I set the transform on the camera as a translator and move it back 4. Actually, this should be 1, really. 100 is way too big for a sphere radius. Okay, and then here I am creating a point light. And here's the intensity of the point light and RGB values. And then here I actually move it back -10, -10, -10. So, so it's kind of in the top left corner towards us. And then here here's just a simple Boolean tester. I just loop over the X and Y values of my canvas. And I generate an array. And here, if I find any intersection, I set it white. And if I don't, I set it to black. Let's maybe jump over to, I put this in CodePen. I know it's kind of brutal because it's 1,000 lines in CodePen, but it is nice if you ever want to, if any of y'all want to play around with the code. So yeah, where's our tester bit? So this is actually our rendering bit. We'll come back to that in a second. But yeah, our tester code. This is good for just checking if you can properly intersect with an object in the scene, right? We basically, we loop over the XY values of the pixels, and then we generate an array at that pixel using the camera, and then we check if it intersects, and if it does, we set it to white, and if it doesn't, we set it to black. So if I run that, should be a white sphere. Yeah, so you can see we actually intersected the sphere. And I had to make it kind of tiny. I had to make it I made it 100 by 100 because CodePen has a nasty feature that it'll automatically detect an infinite loop, and which is good because you don't want to go check out a CodePen and have it crash your entire browser. But unfortunately, it does kill our nested loop because if I made it 300 by 300, that's what, 9,000 iterations. It cuts it off at a certain point. So it's kind of a tiny image. Anyway, let's step through this code. So here, very similar, we're iterating over the X values, iterating over the Y values, generating array. And here we're finding the intersection of that array with an object in the scene. And if it's null, we set the pixel to black and then continue, just go to the next loop. And if it's not null, then we get the surface geometry from the shape. We get the material from the shape. Here we just set we initialize a pixel value to black. We iterate over all the lights in our scene. We get a light vector array for for an individual light, the amount of light that's hitting the object at that point. And then we iterate over those light vectors. We create a shadow ray. So we want to just check, the shadow ray starts from the point of intersection and goes in the direction of the light. And if it basically doesn't intersect anything, then we're good. And we use the material to calculate the amount of color that's reflected from the light toward the camera. And then we set the pixel, we add that to the pixel color. This is if we have multiple lights, right? And then we set the pixel to that color. So let's say you get this nice little sphere. So that was a lot of work just for one little image, right? But the really cool thing about ray tracing, and why I love it so much, is once you get the fundamentals down, it's so fun to add additional features on, and there's so many things you can do with them. You can add additional light sources, you could add additional objects to intersect. I wanted to show you all just really quick,
so for this one that you've got, are you going to add more shapes and whatnot?
I don't know. I kind of miss operator overloading, honestly. Because it's operator overloading is so convenient with these, working with colors, especially.
Yeah, it's super useful.
because you don't have to write dot add and dot multiply. You can just write the operators, and you can. It's also really nice for vectors and normals and points and stuff like that, like just doing arithmetic on them. So yeah, I might continue working on it, expanding it, but I don't know. It was just trying to test it out and see if it was
How performant is it?
I'd say it's pretty bad. I'd say it's pretty bad.
I mean, there's bad and bad when it comes to this sort of thing in JavaScript, but yeah.
Yeah. I did implement one version that used request animation frame. If y'all don't know, request animation frame basically it's the easiest way to run something as quickly as possible without crashing the browser. Because if you just write a really long loop, it'll just lock everything up on the page. So this does work, and it'll do it line by line basically. But
well, that's pretty cool.
Yeah, it's really, really, really slow though. So yeah, doing a double for loop's a little more efficient. But I don't know. There's advantages to using JavaScript. Obviously, I could build an interface around this. A nice web interface, and people could click and add objects and manipulate it or something like that.
Yeah, I had a project a while ago where that was the big choice. Do I offload it onto the user's client to do things, or do I put it on the hosting servers? To decide, where is the load going to go that is going to get done most efficiently.
Yeah. Yeah, JavaScript's kind of annoying to work with sometimes.
I'm just curious though, if you don't want to do this on CodePen, is there a way just to put this into an index.html file and do it on from your local environment?
You have to build it. So I actually have a little bit. I was going to post this link if you guys want to check out TypeScript and how to build it into an actual project. So basically, you need to run. I don't know. I was messing around with it for a while. It's a little bit confusing, but yeah, you can install it using npm, and then you just basically use tsc to compile the file. But then I think you might need something like Webpack to put it all together. So yeah, you could, but it's a little tricky. I also wanted to share some other cool projects with you. This is one of the coolest things I found ever. I don't know how it works so well. It uses WebGL, which is basically it's a web interface to your graphics card, and it uses path tracing. And it's just, whoa. It's so fancy, dude. So fancy. Anyway, and then I also found this one is really cool. This is a two-dimensional ray tracer, and you can actually you can bounce it around objects in the scene. I've tried to implement a 2D ray tracer. It didn't turn out nearly as cool as this. This is pretty amazing, but I think this actually uses the GPU as well.
It looks like they've got. I can't tell if they're faking the color splitting there.
I think it's real. I think it's real. I don't know how they do it. They even have, you can change the emission spectrum.
Wow.
It's pretty fancy. Here's that ray tracer that fits on a business card that I mentioned. I don't know. Don't ask me to explain that. But it actually renders that, which is cool. That's pretty impressive. And there's some good tutorials on the internet. This is the actual tutorial that I used when I was learning ray tracing. It's pretty old, but it's actually, I think it uses C++. And you can download all the code in C++ if you want, and it's pretty good. It's pretty good. There's this great book that was called Ray Tracing in One Weekend, and I think this guy's actually made multiple ones at this point. You have to pay for it, but it's like $3 or something. I don't know. Yeah, you can buy it for $3. A really good reference is Introduction to Ray Tracing. This is the classic one. It was written in 1986. It's so good though. So this covers like all the basics. And then there's also PBRT, which is like, you know, if you want to devote the next few years of your life to ray tracing, this is the book for you. It goes all into like physically based rendering, which uses a lot of like very advanced statistical algorithms and a lot of like physics-based equations. So I've implemented a physically based ray tracer. It's not for the faint of heart. But anyway, I'll post all those links. I think I'll probably put them in the repository that I linked to first. Here in the, I'll link them in here in a README or something like that. Cool. Any questions on it? It's already 6:10.
I have one conceptual question, I guess. I don't know if anybody has an answer to this. Is ray tracing and rasterization is that how solid modeling programs work behind the scenes? Like,
you can do, I don't think so. I think those probably work with meshes. You can do what's called a constructive solid geometry with ray tracing. Basically, you can build up objects like this using by composing them using smaller objects, and you do Boolean operations on like the segment that intersects an object. So yeah, constructive solid geometry is one way of doing it, but they probably use meshes. That's my guess.
For rasterization, it's meshes, and the real difference between the solids and the meshes is whether or not they have an actual inside. And rasterization generally uses the meshes, and ray tracing generally uses the solids like the CSG. Like there's a software, PopRay, and they're really big on the whole constructive solid geometry stuff. But the big thing is when you slice a mesh, it's just it's a facade. It doesn't have an inside, right? But when you slice like a solid, like when you're doing in the CSG, it ends up creating these new surfaces, and the thing maintains its I guess what I want to call coherency. You know, it maintains its life as an object instead of just being, you know, instead of making it obvious that it's some sort of, you know, magic that's going on there.
Yeah, so I'm not sure what CAD uses. That answers your question. It
depends on the CAD package.
Okay, cool.
Some of them are solids. Some of them use message like Rhino 3D. It uses it largely uses NURBs, which are they're not meshes, but they're the same kind of thing. They don't have an inside really.
Yeah. That's cool.
And I know there's some, especially some toy CAD ones that that's what they're built around. It's like the same thing with this is built to explore the this TypeScript thing was built to explore TypeScript in ray tracing. There's people who developed their own you know, CSG packages, CAD style CSG packages to explore, you know, that in a CAD format, so they could see where they could go with that.
So after all that time, that thing is still rendering. Wow.
It's pretty slow. Well, I think the JavaScript stops when you leave the tab.
Yeah, I think request animation frame depends on whether or not the tab is open.
Any other questions? I'm gonna like throw a bunch of links in the chat if anybody wants to check these out. Stop sharing my screen actually. Questions? Cool. Thanks everybody for coming. That was a lot of fun. Glad to share my love of ray tracing.
How long have you been I know you mentioned it somewhere, but how long have you been working on ray tracing kind of stuff?
I'd say I took a fair break for a number of years. I mean, I started in high school. I think I
Yeah.
was a junior in high school, and I started playing around with them.
Cool.
Yeah, and then I quickly went into I got really into hyperdimensional geometry. I actually have a hyperdimensional ray tracer implemented in JavaScript if anybody wants to see that. It's a little bit.
I saw, what was it? It was one that takes into account how things look as you approach light speed.
Oh yeah, I remember.
There's like some kind of temporal thing going on there.
Mm-hmm. Like it would get blue as you move toward things and red as you went away.
Yeah, it's not just that. It's like things start, stretching out or moving around and stuff as light takes a while to get to you.
Yeah. Yeah, there is. Oh God, what's it called? The Lorentz transformation.
Yeah.
That's actually, you can use that in a ray tracer pretty directly. It's pretty cool. You can just transform the XY coordinates.
I think the thing that really blows me away is that one with the where the one you showed earlier with the light splitting.
Yeah, that's really cool. Okay, so my links.
Okay, so I have to ask, what's the difference between a ray tracer and a physically based ray tracer?
So physically based ray tracers try their hardest to recreate actual scenes, like how things would look in real life.
Gotcha.
So you can do really cool things. There's something called a BRDF, bidirectional reflectance distribution function, and the BRDF is basically a probability distribution that captures given the incoming ray and the surface normal, what is the probability of generating a ray in any given direction. So, and you can actually measure the BRDF of real surfaces using something called a goniometer. It will basically I'll look it out here. Let me share my screen again. Goniometer. Glad I spelled it correctly. That's not it. Come on, that's what it is. Where's a better graphic? Oh man, here, that's the best graphic probably. You basically measure the reflectance for all incoming angles and all outgoing angles. But it's so cool because you can model things like Velvet. Velvet has what's called backscattering. So light will actually be reflected back at the source.
So it seems like they're basically brute forcing that.
Yeah, you basically generate a huge table of data. And then, but you can, it's so cool because you can take real world physics and put it directly into a ray tracer and then just look up the values of the reflectance for the given incoming and outgoing angles.
Huh.
So there's that, the BRDF. There's also something called spectral power distribution. So y'all have heard of what's it called? Dispersion. Dispersion is basically it's the Pink Floyd, Dark Side of the Moon. You have the prism, and you have the white light coming in, and it gets split into its different components. That's because different frequencies of light have different indices of refraction. So blue light will refract more than red light, and that's basically it's very difficult to capture with RGB color. But there's something called the spectral power distribution, which is basically the x-axis is the wavelength and the y-axis is the intensity. So And you can have more samples than just 3, because 3 is really limited. You could have like 100 samples across the spectrum. And you can actually measure these things. You can use what's called a spectrometer. And a spectrometer can measure the light or the reflectance of a real world surface. And then you can take that and put that directly into a ray tracer. So there's a lot of really cool, and you can do things like Rayleigh scattering. Rayleigh scattering is the reason why the sky is blue. You can capture that in a ray tracer as well. So there's so many cool physics things you can do.
I kind of really wish I had studied more of the optics and stuff when I was in engineering. This is impressive.
Mm-hmm. Yeah, it definitely gets fancy. All right. I actually have another meeting I have to go to. So it's been great. Thanks for coming, everybody. I hope you come to future tech talks. We're trying to do it like once a month. I'm gonna turn on a light really fast because I don't feel like being.
Well, that was pretty cool. I'm looking forward to the next one too.
Okay, geez. Yeah, I think we'll do the future ones. I think will be. I don't know. I have a few ideas of doing them on like some web development stuff. So building single page applications. I don't know. There's a lot of fun stuff we can do.
I hear that. That's what I'm specializing in, so to speak.
Cool. So yeah, keep in touch. Always feel free to reach out to me. It's Matthew@pdxcodeguild.com. I'll put that in the chat. If you have any questions about anything. We also have, Peter, are we still doing the Monday Night Python?
I think we are, because I'm blanking on who was hosting it, but I think he's still doing it.
Cool.
Yeah.
It's like a weekly meetup, just virtual on Zoom.
It's on the same meetup network on the meetup.com page.
Mm-hmm. Is that the one with Michael Flynn?
Yeah, Mike Flynn. Yeah. Cool. Yeah, thanks for reminding me of his name. Like I talk to this person every week.
Cool.
I was going to ask about that though. So is that strictly Python or is that other languages as well?
It's just a tech hangout. I mean, it's kind of Python themed, but you can talk about anything. And
Cool.
we take all kinds of programmers.
Cool.
Yeah, check it out.
Yeah, last time we were doing something in JavaScript, but it could be Python. It's Python-ish.
I like that. Cool. Again, thanks everybody for coming. It's a lot of fun talking to y'all, sharing my knowledge of computer graphics. I'll see y'all next time.
Thanks.
Thank you.
Have a good night, everyone.